Here we go. All right, so first one, identify all the compounds that contain a carbonyl group. This was A and B. A lot of people that got this wrong said D, but D is not a carbonyl group. It's actually a carboxyl group. When you have the two oxygens next to the carbon, that's a carboxyl group, and it actually does have different reactive properties due to the double oxygens being next to the carbon. So that's just A and B. A lot of people did very well with the table. I was hoping with the homework assignment that I'd given you that you would get a chance to review this. And so for Tollens reagent, we were just looking for the aldehyde, and the observation is a silver mirror. For alkaline solution of iodine, this is the one that people forget a lot. It's CH3, CHOH, or CH3, C double bond O. These are the two different possibilities that you have a reaction with iodine and NaOH. So it would have looked like I2 and NaOH last year. And so this one identified A and C. And the correct identification, you would get a yellow precipitate. You could say pale yellow, but the pale was not required. So that would be that one. And then finally, sodium metal reacts with carboxylic acids and alcohols. So C and D. And this is fizzing, bubbling, but I didn't see anybody write effervescence, which is Cambridge's. You did? You wrote effervescence? Okay. That's Cambridge's favorite one, effervescence. So fizzing, bubbling, or effervescence. And so that was actually, this comes from the 2019 test. And I'll never forget that one because the students came back from that test saying, oh my gosh, that test was so hard after paper 2. I got a hold of the test, like, after the 24 hours, and I was like, it was not hard at all. Why did they say it was so hard? And we started going over the answers, and they're like, I put that. And I was like, so was it that hard? And it did really well. They ended up, a lot of people passed it, but it was like, they came out of the test being like, oh, this is so hard. Like, what is chemistry? It's not easy. But this is wild. 8 marks for that is crazy to me. Like, I think they test more difficult now than what they did pre-COVID. I think the pre-COVID tests were in some ways easier. All right, both ethene and benzene react with bromine. What type of reaction is bromine with ethene? Some of you put the full mechanism, but all you had to say is that it was addition. So if you wrote the wrong type of addition, which was the wrong type of nucleophilic addition, they usually would just ignore that and just look for the word addition. It was electrophilic addition is the right mechanism for it. So what we're going to learn today is that benzene does not do addition reactions, at least not most addition reactions the same way that an alkene does, because benzene is no ordinary alkene. Due to, in lesson 1, we learned about the resonance of benzene, that the double bonds are actually delocalized all around the structure. This actually changes benzene's reactive characteristics. And so benzene will have its own series of reactions. I know you're so excited to learn about all the reactions of benzene. Today, we're going to cover a lot of reactions, actually. We're going to cover electrophilic substitutions of benzene. We're going to talk about electron withdrawing and donating groups. We're going to talk about special reactions of benzene. I think I did a quick count last night, and it was like 7 if we get through everything. 7 reactions and 1 mechanism. In your flashcard paper that I gave you, I went through the syllabus last night, and just like I did for you for AS Chemistry, I found every reaction in this unit so that you could track along to make sure that you're covering in your flashcards every reaction that we go over. There's a series of 24 this year. Just to give you an idea, last year was 30. But I actually think this year's the same, but we put some of them into Unit 5. We did hydrolysis, condensation. We did that in Unit 5. So it probably was about the same amount of reactions, but this year organic's been split into 2. We did part 1 already, and now we're doing part 2 of organic. And so there's 24 reactions this unit. There are 2 mechanisms. Last year there were 30 reactions and 5 mechanisms. So that's why I said it's less, given that I broke the units up into 2, it's less in this unit. However, it's still a lot, and it's going to look like a lot because benzene rings are big. So you're going to see a lot of big looking molecules doing reactions. So with your flashcards, if you have the time in class, you can start filling them out. If you don't, that's your responsibility to go home and do. That project, the flashcard project, is due on the day of your Unit 6 exam, which is at earliest April 8th. So it's not for a little while. So with that being said, these are our objectives. It looks like a lot. Organic will always have a lot of objectives to go through because most of them are fast. We'll be looking at substitution reactions with both benzene and methylbenzene. We'll be looking at a mechanism today, if we have the time, for electrophilic substitution. And like I said, we'll be looking at something called inductive effects to find out if we have an electron donating group or an electron withdrawing group. So before we get started, this is actually from AS Chemistry. This question right here is from AS Chem. And it asks you to do the electrophilic addition mechanism. So let's see if we can go back through the steps for this mechanism. The first thing you would do is you put a dipole on this molecule, HBr. Which part would be positive and which part would be negative? Hydrogen would be positive and the bromine would be negative, right? And then what has to happen? We know in the end we have to get both H and Br on here because what an addition reaction is. You break up the double bond and you put one atom on each side. But what happens next? How do we get these atoms onto this organic molecule? Isa.
Put the negative charge in the double bond.
Okay.
And draw an arrow from the thing to the.
So you're going to draw an arrow from the double bond, those 2 electrons grabbing the hydrogen. But hydrogen cannot both be connected to this molecule and be connected to bromine. So a bond has to break. What bond has to break? This one. And the 2 electrons go to bromine. Now you have to decide, does the hydrogen add to the left-hand carbon or the right-hand carbon? Does anybody remember? Because this is not symmetrical. So does the hydrogen go here or does the hydrogen go there? Left or right?
Right.
The answer is the right.
No.
Why?
I know.
Because the left hand gives you a more stable carbo-cation, and that's what we called, Markovnikov's rule, or the inductive effect of neighboring carbon groups. That is going to be the carbon that's deficient an electron, the one that's got more carbons around it. And this is where the hydrogen group will go. And so now what do we do? Almost done. One of these lone pairs does occur in the node of the carbon and makes your final product. This was called the electrophilic addition reaction. It works with alkenes and any type of XY small molecule. It works for any type of XY. So it could be HH, it could be HX, it could be XX, where X is a halogen. It could be HOH. Electrophilic additions work with any of these types of additions of 2 small parts of a molecule. So hydrogen was called hydrogenation, water was called hydration, and then you had the halogen alkane, like either double halogen or like we saw here, HX. So benzene doesn't do this. Because with benzene, because the electrons are delocalized around the ring, you can't just take the 2 electrons to grab an atom. And so benzene will undergo a different series of reactions than regular alkenes. Yes, Athel?
Do we include the negative charge on the bromine?
Because I have the 8 electrons there, it's probably unnecessary, but if I didn't write the 8 electrons, you should write the -1 charge. The key is writing the arrow starts at the pair of electrons and goes to the carbon. That's where the mark is always at. All right, so that is one mechanism. In your homework, you had another mechanism. It was a nucleophilic substitution. Today, we're going to learn a whole other mechanism. And just a reminder, mechanisms tell how the reaction takes place. How did we get from the reactants to the products? And so before we start our reactions, I actually was thinking about this last night, and I'd already printed this out, but I think I want to talk about electron donating and withdrawing groups first. So change to slide 10. Right here. Because this is going to go a little bit off of some of the things I was saying back in lesson 1. Electron donating groups. So what we're talking about here is groups that are already present on the ring. So if you have a methyl group on your benzene ring, which is called methylbenzene, like this. This is called an electron donating group because it donates the electron cloud into the ring. It's also called a ring activator. It's not really a word that Cambridge uses, activator, but it's a word chemists use. It activates the ring, makes it more reactive. And specifically, these are directing groups. And what do I mean by a director? If you have a director in a movie, what does the director do? They tell this person to go there. They tell that person to go there. You have to be positioned like this for the scene you're going to play. And so by director, it means that this group, because this group is present, it tells the other groups that are going to get added in that they have to go to positions 2, 4, and or 6. Depending on what group you actually have there, you could actually have groups add to carbons 2, 4, and 6. We're not going to see that today, but we might see that on Thursday if we get through all of phenol. Yes.
So this is at the bottom going into it.
Ring activator. So it activates the ring. So basically the idea is that if this group is present, then new groups will add, this is carbon 1 of the ring, 2, 3, 4, 5, 6. Or you could go clockwise or you could go counterclockwise. So that means that new groups will enter 2, 4, or 6, those positions specifically. So that's what I mean by director. What are the electron donating groups? The electron donating groups are methyl groups. They are alcohol, ether, amine, and amide. Those are the electron donating groups. And typically to be an electron donating group, it has to have a pair of electrons that's being donated into the ring. Or it's an alkyl group, a methyl group that donates into the ring because of the inductive effects. Yes, alpha. Yeah, you can use the restroom. Schedule and go. All right, so that's electron donating groups. That means the main one you're going to see is methylbenzene because if you looked at the objectives, it said to compare benzene with methylbenzene. So this is the main one you'll see, but you'll also see these other groups. Bad news. What do you think is falling after bad news?
Memorize.
These should all be memorized. These will not be given to you. They actually used to give this on the data booklet before 2022. But they took the data booklet away and they do not give you this in new questions. So that means that it's now become something that you are expected to know. And like I said, for me, when I was learning this, I kind of reasoned it out for the most part. I could figure most of them out because it was like, okay, it's either methyl groups, like a bunch of carbons, or it's something that has that lone pair of electrons that could be donated into the ring. And that's what is characteristic of these groups. A single atom that has electrons that could be donated into the ring. Now, there's a difference between these and something called electron withdrawing groups. So donating means that it donates into the ring, donates electron density into the ring. Withdrawing, what do you think that means? Takes electron density out of the benzene ring. So basically, instead of electrons being donated in, For these groups, they'll actually, so like if I have an NO2 here, actually electron density will go out of the ring and towards that group is the idea. And this happens, generally speaking, when you have a lot of electronegative atoms. So you have a great density. There are certain groups that you just have to remember. So NO2, that's one. That's nitro, the nitro group. Carboxylic acid, that makes sense to me because that's super electronegative. It's pulling electrons out. Esters pull electrons out. Nitriles, aldehydes, and then NH3. These are what we call the electron withdrawing groups. So NH3 plus is an interesting one to me because NH2 is electron donating, but NH3 plus is electron withdrawing. And the reasoning, there's no lone pair to be donated in NH3 plus because everything is bonded. And so what happens is you've still got that electronegative atom that is pulling the electrons out, but nothing that's donating in. So that's why NH3 plus is electron withdrawing. Electron withdrawing groups, so they withdraw electrons from the ring. And this is also called deactivators. So they basically deactivate the 2, 4, and 6 positions. So they deactivate the ring, which technically makes it less reactive. But if it reacts, directs to the 3 and 5 position. Which means where? If my NO2 is here, where's 3 and 5? Here or here. So that's where your electron withdrawing groups will direct other groups to. And so I wanted to bring this up before we even started the reactions because Cambridge wants us to compare benzene's reactions versus methylbenzene's reactions. And in order to do that, you have to know that methylbenzene is electron donating in nature. And again, these would have to also be memorized, the electron withdrawing groups. Three, 5 position. All right, so now that I brought up what's going on there, we're going to start back on our reactions. So we're going back to slide 6 so we can start to see what are the reactions we're expected to know. So these are going to be flashcard reactions. The good news about electrophilic substitutions, which we're about to see, they almost all do the same thing. So it's just what am I adding in is going to be different. So very much like the addition reactions. The addition reactions we saw earlier, they all add in the same type of molecules. It's just the specifics is what you're looking for. So back to reaction 1. Reaction 1 out of the 24 that you have to know for this unit. This is a benzene substitution reaction with bromine. So this would be something I would be putting on a flashcard. Reactants and products. And so why is it a substitution? I'm going to go ahead and draw out all the hydrogens here. Because benzene is C6H6. And all the hydrogens here. Why is this called a substitution? Isa.
Because the hydrogen, no, the bromine replaces the hydrogen. And
Bromine replaces the hydrogen in the ring. But wait a second. Isn't a hydrogen and carbon bond pretty strong? How does that happen? Like it's like the carbon hydrogen bond is nonpolar. So how does that happen? The mechanism will help us out with that, which is why we discussed actually the mechanism on day 1. So conditions, special conditions. You need a catalyst. The catalyst can either be with a transition metal iron or aluminum. So it's either FeBr3 or AlBr3. So one of those two will be serving as a catalyst. And then the type of reaction is called an electrophilic substitution because you're going to be adding an electrophile into the ring. And we'll see how that happens shortly. Yes.
is this one of those reactions where we have a carbon with 5 bonds separately?
I don't think so. No. I don't know. I mean, we'll see the mechanism and you tell me if you think that carbon has a 5 bonds at any point, but I don't think so. Comparison with methylbenzene. So this you're going to want to be aware of. If I have methylbenzene and I'm doing this reaction, So let's say that we had Br2 and AlCl3. Where are AlBr3? Where would the bromine be going? It says positions 2 or 4. So what does that mean? It's either going to go here or here. Why don't I say 2 or 4 or 6? Because I was intentional about that. 2 and 6 are the same. They're both one away from the CH3. So if I'm just getting a mono substituted product, one substitution, then it's either going to be right next to the CH3 or across from the CH3. And so that's because methyl, like I mentioned, was an electron donating group. So you are supposed to recognize if you see an electron donating group, how that group would substitute in. And if I see an electron withdrawing group, how the group would substitute in as a result. And so that's reaction number 1. It's a flashcard reaction, 1 out of 24. Remember, for your flashcards, you're going to want a total of 3. 1 with the name of the reaction and the general reaction type. 1 for the conditions. The conditions here are the catalyst. That's what you specifically need. And 1 with an example reaction, which I've given you a couple here. Yes, Isa.
Is there a major and minor product or both?
They're equivalent. Equivalent products. It's a good question. You get a mixture is the answer,
Is there a
which means you have to, figure out how to isolate that mixture. All right, so that's reaction 1. The next one says 1B, but on your flashcards, it's technically reaction 2. Reaction 2 is actually almost exactly the same as reaction 1. It is still reaction 1B. Substitution with chlorine. Same thing, but instead of bromine, now you're doing this with chlorine to get chlorine onto the ring. So you need, for Cambridge, they just need you to know the AlCl3 catalyst. I think this is interesting, dry conditions and hydrous conditions, but you don't have to state that for Cambridge, just the AlCl3 catalyst, and that'll be super important as we get to the mechanism. And then if it's methylbenzene, you see this again, 2 or 4. And there is a byproduct of HCl, and we will see the byproduct when we do the mechanism. So that's 1B, which is still substitution with a halogen for a hydrogen. Now, the next reaction, this is officially a new reaction. What if there's UV light instead? And not a catalyst? Because technically, this is something we did in AS. What would you do if there was UV light in Cl2? Adds up. Where?
Does it like break the double bonds and add Cl?
Nope. It's not what UV light does.
The methyl.
The methyl group. So basically, UV light is your cue that you have a free radical substitution, which means that the halogen is actually going to react with the side chain. Not the benzene. And so what do you think this product could be? Instead of CH3, it could be CH2, Cl, plus HCl. Because it's a free radical substitution, is that the only product we could get? No, you'd actually technically have the possibility of a plethora of products. You could have 4 CHCl2 or CCl3, right? You get a plethora of products because free radical substitutions can keep propagating. So it can keep propagating with the side chain. So that is technically a reaction you probably should write down because it can show up, but it's technically not new for the A-level standards as it was from AS chemistry. Yes, Peter. Doesn't matter. The same. Yeah, they're all equal. Like technically,
Even if it was that, you still have to do rotations, so it's just mirror.
technically that is what you have. Because these bonds are transients. They're moving through. The pi bonds alone. The electrons are moving through all of them. So it doesn't matter how I do the double bonds here, which is why it's better to just write the circle a lot of times. However, when I was a student, I wanted to write the double bonds in because it helped me with octet rule.
Mm.
And not having octet rule violations. Okay, so reaction number 2, nitration of benzene. This is another electrophilic substitution, and this one is a little wild, and you do have to memorize the conditions. This is how you put NO2. So if somebody was trying to make TNT, this would be a part of their process. They would have to put, they'd have to nitrate it. They have to put NO2. And in order to do that, you actually need very specific conditions. You need 55 degrees Celsius, which is pretty hot. In the 140, 50 degree range, I think. You can look up. And concentrated nitric and sulfuric acid. You need a mixture of concentrated nitric and sulfuric acid, actually here. Both are required. Don't think so. So comparison with a methylbenzene. With a methylbenzene, you're still going to get the nitro group into position 2 or 4 because it's an electron. Methylbenzene is an electron donating group. So just as a reminder, if I had this and if I had CH3 here, I would, with HNO3, H2SO4, and 55 degrees Celsius, I would have a mixture of products, this or this. Right. Either to the 2 or the 4 position. And then we'll see exactly how that works because we want to see the mechanism for this too. And so this reaction is another one that goes on flashcards. It is a substitution where you are substituting out a hydrogen or an NO2. So everything we're doing today is electrophilic substitution, except for like some of the random side reactions. Yes. Yes.
Okay, do we specifically have to write 55 degrees Celsius? Right?
Yes. That's actually a requirement from Cambridge. They want you, I don't know why they want you to know. For most reactions, they're just like heat. For this one, they're like, no, it's got to be 55 degrees Celsius. Specifically. Control that temperature to get the night NO2 on. There's another reaction later this unit that you have to specify that has to be cold, but not any cold. 5 to 10 degrees Celsius. They're like very cold. Yes. Yes, it could be 6 or 7 degrees Celsius, but 5 to 10. Yes. I would put both because you will be asked possibly for all possible products on many assessments. Because remember, you will be assessed on practicing with organic reactions because you're going to have a bunch of them. And the best way to get better is to do a lot of practice. Okay, so let's take a look. I've already talked about electron donating and withdrawing groups. Let's just take a look at a couple questions from the textbook or from revision, wherever I got this. Draw the structures of the products formed in these cases. I've got one chlorine atom substituted into this benzene that has NH2. So NH2. Where would I put the chlorine? How would I know? Does the chlorine go to 2 or 4, or does the chlorine go to 3 or 5? Chlorine goes to 2 or 4. Why?
Because NH2
NH2 is, and I don't want to write all those words. So are you good with me writing EDG? Electron donating group. I don't think you can do that for Cambridge, unfortunately. I mean, you have to say electron donating. I've never seen them use EDG in a mark scheme. That's how you know. But I don't want to write all that. So why NH2 is EDG? So what would my possible products be? The Cl can go here, or what's the other one? My other one. Chlorine goes where?
Middle.
At the bottom, directly across. In future organic classes. So for any of you who pursue additional chemistry beyond this point, 2, 4, 6, and 3, 5 notations are not used, and I wish they would because it makes sense. Like how far you are from the group, they use this notation instead. So if you have, let's say that your Y group is 1 away, this is called the ortho position. If you have your Y group is 2 away, this is called the meta position. And I was hoping this wouldn't show up on the Olympiad. It didn't last week because it's called the ortho position, the meta position, and then the one that's directly across, like this, is called the para position. And so it's actually ortho meta para or OMP on. That's how most chemists will refer to benzene rings. And then this should be incorrect. You can have multiple ortho meta para positions, and they use it for naming. Meta. META. The meta position.
That's why it's like my back so far.
And so this designation is used by actual chemists. This is not used by Cambridge, but if you were to take any future organic classes, you would note that a 246 director is an orthopara director. That's how I remembered it. And a 35 director is a meta director. Yes.
What does the one farthest to the right say?
This one?
Mhm.
Para,
Para.
the para position.
So EDG, what does EDG stand for again?
Electron donating group. All right, so let's try the next one. 2 NO2 groups are substituted into methylbenzene. So what they're saying here is we're putting 2 in the same benzene. We're forcing 2 NO2 groups into benzene, methylbenzene. Where do they go? Who's the director? The CH3 is the director. And is it a 246 director or is it a 35 director? Methyl?
Oh my god.
246?
Yeah.
So it would be NO2 groups goes to 2 and 4 or 2 and 6, right? Because you're putting 2 in, so different combinations. Because CH3 is an electron donating group. That's the director. So your possible answers are NO2, NO2, and NO2, NO2. Those are your different variants. Either both are 1 away or one is 1 away and one is across. And what about this next one? 2 bromine atoms are substituted into benzoic acid. We've got benzoic acid. How should the bromine atoms be added? Should they go 2, 4, 6 or 3, 5? 3, 5. So the Br would be added to 3 and 5. Why? Because you're looking for what is carboxylic acid doing? Is that electron donating or is that electron withdrawing? And carboxylic acid is definitely electron withdrawing. And so we go here and here. So that's the concept for how to do your substitutions, using electron donating groups and using electron withdrawing groups to help you with that. So now that we've seen our basic reactions, we are going to take a look at how does this happen. That's called the mechanism. Go ahead.
So when you say also and
For the third one? For the second one? And means you have to write both of them. all possibilities. You have to put all the possibilities of how you could add two two groups in there that are unique from each other. All right, so we've taken a look at a few reactions, 3 so far, and now we're going to take a look at the mechanism for how does this happen in the first place. How does the hydrogen get out and the other group go in? And this is called the electrophilic substitution mechanism. Now, I am so used to calling this something slightly different because it's how I learned it in university. Not very different, but I do want to say how I learned it because I'm going to say it often and it's not wrong to say it. And I think that the way that I learned it in university is better. So I learned it as electrophilic aromatic substitution. Why do I think that's better? Because it tells you this happens with benzene. Because aromatic is benzene. So this is electrophilic aromatic substitution. It helps you differentiate that it's not the electrophilic addition that we learned back in regular alkenes, but that something different is happening specifically when we have benzene. In your flashcard notes, I put this as EAS because I don't want to write it every single time because it's a lot of letters. I don't love to write a lot. So electrophilic aromatic substitution. These are the steps. We are going to first have to generate the electrophile. And this is what we use the catalyst for. The catalyst helps us get the electrophile, which is going to be E+. So you first have to generate the electrophile. Once you, and yes, that'll be a mark. There will be a mark for showing how you generate the electrophile, and I'll teach you how to do that. And then once you have generated the electrophile, you have to remember about reactions, the following, that the 2 electrons of the double bond are going to go grab that positively charged entity, the electrophile, essentially temporarily breaking the benzene delocalized system, actually. And so instead of having 3 double bonds, you have 2 double bonds. And then you have a negatively charged entity that goes and grabs the hydrogen with this 4 bonded carbon, not 5. And that hydrogen, the 2 electrons from the hydrogen fold back in to restore the double bond with the ring. And this is the concept of how it happens. Now, like usual with the mechanism, I'm going to show it from scratch. This is one that's already been pre-done for you. I have a couple of them here to go through. You'll see my notes take a lot of space. But I printed these 2 per slide for a reason, because benzene rings are big, and you're going to want to have space to do this. This I picked up online. It says attack of the electrophile by the aromatic pi bond. Step 2, I want to highlight this word deprotonation. Cambridge doesn't really use it, but chemists use it. What does that mean? Yeah, it just means remove hydrogen. Whenever they say proton, they're talking about hydrogen that's being taken away. Specifically H with a plus charge. Because you take hydrogen, but you don't take its electron. The electron goes back into the ring. You're technically essentially taking H plus. That's why it's called deprotonation. Protonation means add, deprotonation means take away. All right, so with that being said, let's take a look at a Cambridge question, how we would create this from scratch. Electrophilic substitution reaction. Bromobenzene can be prepared from regular benzene as shown. Name the mechanism. So first of all, the official Cambridge name for the mechanism is just electrophilic substitution. Electrophilic, I'll put here aromatic. You do not have to say that. It's not wrong, but you don't have to say it. Substitution. And then we are asked to draw the mechanism for this reaction, include all relevant curly arrows, any dipoles and charges, and it's worth 4 marks. So 5 marks altogether here. I have where the marks come from? So mark 1 is to generate the electrophile. So how do we do that? How do we generate the electrophile? Well, first of all, what is the electrophile going to be? If we look at here, what is going to be going onto the ring? Go ahead. A positively charged what?
In the species.
Yeah, but what species here would be positively charged? No.
Yeah.
Bromine. Because at some point, you have actually got to get this onto the ring, right? So you have positively charged bromine. So how in the world does that happen is the question. This is what you need the catalyst for. So I'm going to write it on the side and then write exactly what Cambridge wants you to write over here. So how does this happen? Let's take a look at AlBr3. AlBr3. And we put that with Br2, right? So what is even happening here? AlBr3. Aluminum has an open slot to receive electrons. All right, do you agree with me so far? Aluminum can have 4 bonds, not 3. And technically it would prefer to fill its octet. That's why AlCl3 becomes Al2Cl6, because you can merge 2 AlCl3s together. So what happens is the following. These 2 electrons go here. And you have this. Al, Br, 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 But this actually isn't stable. So what happens? These 2 electrons, and so this actually gets a partial negative charge, a partial positive charge, like that. These 2 electrons actually go here to this bromine. And so you end up with Al, Br, 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 plus Br with 6 electrons. So what does that mean?
Bromine cation.
A bromine cation. And what does that charge have? AlBr. 4. What charge would that have? Not positive. It's actually -1. Because the aluminum has 4 bonds instead of 3. So we learned about formal charge last week. If it has an extra bond, that means it has an extra electron. And so this would actually have a -1 charge, like that. So that's the full process. Cambridge does not need you to know all that. Like, they don't expect you to write all of that to earn the 1 mark. So how do you earn the mark? Generate electrophile. This is what Cambridge expects you to write. But I think it's important for you to have, general understanding. If you need to know, like, this is how this happens. This is how this happens. Okay, this is what they want you to write. Br2 plus AlBr3, and they just want you to know this happens. It becomes AlBr4 minus the aluminum grabbing the bromine. And then because this is minus, this other bromine has to be positive. So you generate your electrophile there. Br plus is your electrophile.
Oh my god.
So this is what you would write for the 1 mark. That's mark 1. So once you have generated your electrophile, that's 1 mark out of the 4. Now we can actually do the reactions. And so the reaction is to take our benzene ring. Do you want to do circle or 3 double bonds? Okay, so I'll show you how Cambridge wants you to get the marks with the circle, which is actually easier. Circle plus Br plus. That's what we have, right? We showed that we make Br plus. Now this is the electrophile. So electrons are negative and the bromine is positive. So the next step is for 2 electrons in the ring to grab that bromine. Like that. Looks like that. And this is the result. This is how Cambridge writes it in the mark scheme. A broken ring with a positive charge, indicating that here we're going to have a hydrogen and a bromine where we added that new bromine in. And on this carbon right here, this carbon only has 3 bonds, so it has a positive charge. That's why for me, I always liked writing the double bonds out so I could see exactly which bonds were broken, but this is acceptable. So we've got this right now. A broken ring that's not completely delocalized, 1 carbon here that has 4 bonds, and 1 carbon here that has 3 bonds is the idea. Yes,
So is the H right there like just the hydrogen that was always there?
it was always there. Remember, all these hydrogens were always here.
Wait,
Yes,
so one of them will have a, wait, this is 4 or 5? There's 11 of them.
one of these double bonds is gone.
And the
The other one right here, this is gone. This carbon only has 3. That's why I said it's much easier to count if you have the double bonds being shown. You don't break octet rule here. Like you have too little, not too much. Yes.
So what's it called? You don't. So do you show like? Do you have to show BR or no?
Yes. That's what you're putting in the ring.
Okay, so you can't.
Yes, you have to show what you're putting in the ring. You have to show the bromine. And you have to show the hydrogen next to it. You don't have to show any of the other hydrogens, to be clear. Just the bromine and the hydrogen next to it because of what happens next. Because remember, the key concept here is a swap is happening. Bromine is going in and hydrogen's getting out. Yes, Francesca.
this is also Mark 1.
I'm sorry?
This is also Mark
No, this is Mark 2. I'll highlight the marks once we're done with the mechanism. But again, you did not have to write all of these. This is just me proving octet rule. Let me erase that. Okay. So this is what you need to have. Now, the thing is now I've got the bromine in, but the hydrogen has to go out. So how does it go out? This is where you use your AlBr4 minus. Comes back in, your catalyst. And so what happens here is one of these bromines actually grabs the hydrogen. And if it's grabbing the hydrogen, where do the 2 electrons from the hydrogen go? Because the bromine's actually bonding to the hydrogen. The hydrogen can only form 1 bond. So the hydrogen's electrons go back into the ring to reform the double bond. And so then you get this. Because the bromine grabbed the hydrogen, it's no longer going to be attached to the AlBr4, so it becomes AlBr3 and HBr, thus restoring the catalyst that you started with. Remember, a catalyst you start with and you end with the same exact thing that you started with. So mark 1 was generating the electrophile. I'm going to write down where you earn the other marks. 2. Mark 2. This is a curly arrow from the ring to the Br+. Curly arrow from the ring to the Br+. That's mark 2. Mark 3. Correct intermediate. That's this. And mark 4. Curly arrow from the CH bond into the ring. You okay? And loss of hydrogen. And specifically loss of H+. Do you need a? No. I'm pausing because the mechanism is actually always the same. And remember that this unit only has 2 mechanisms. Whereas in AS chemistry you had 5, this unit you have 2. And I've analyzed a bunch of old exams. I like to do that. And on about 80% of them, this is the mechanism chosen because it's used for so many different reactions. And only 20% is the other mechanism we'll learn. So this one's one you definitely have to rehearse and study because there's a good chance it shows up.
Can we write the mechanisms for the flashcards?
You have enough flashcards for it? Yes. Axel, yes.
Are we gonna be like creating our own reactions again?
What?
Are we gonna be creating our own reactions again?
What do you mean by that?
I feel like it was either last year or just really early this year where they would ask us to like complete our own like a reaction ourselves without really any help.
I don't know what you mean, but I'm going to preemptively say yes. I'm just going to assume that answer is yes. All right. Check up.
I think you need to complete the reaction.
You mean make the products?
I mean, make everything.
Yes. I'm going with yes. So it will be, if you are thinking about synthesis, where you have to go from this place to that place and you have to take like 3 or 4 steps to get there,
Yeah.
the answer is yes. I'm actually going to use your practice set with beta tests. Because I was reviewing over it. I was going to do it with them yesterday. Tomorrow, but now I'm practicing for SATs, so we'll see about when they get it. But they're going to get that practice set because they need to practice their organic. All right, let's try this again. This time I'm going to work through it without showing the ring. I'm going to show it with the 3 double bonds so you can see how it would be done that way. And so this is going to be chlorine with benzene in the presence of aluminum chloride catalyst. So the overall reaction is we have to go from here to here. That's what we need to do. That's the overall reaction. So the question is, how do we get there? What's the mechanism for this? Step 1 is to generate the electrophile. So what would that be? Cl2 plus AlCl3, and what are my products? AlCl3 becomes AlCl4 minus, leaving fluorine to have a positive charge, which is crazy. All right, so that's step 1. Then step 2 is to do the actual reaction. We've got benzene. This time I'm going to show it with the 3 double bonds and all the hydrogens so you can see octet rule and why the answer is what it is. Plus Cl plus. So this time I'm going to show one of the double bonds grabbing the fluorine. To form a new bond, because right now it's like this, right? So this goes like that. So what you would get as a result is this. Hydrogen, 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 hydrogen. It's symmetrical, so it doesn't really matter. This bond is broken, right? So then we've got a chlorine. It doesn't matter which hydrogen we add it to. Do you want to do the one on the top or the one on the bottom? Top? Okay. It doesn't matter. But what it does matter for is saying where the positive charge is. So where would the positive charge be if that's where I added the chlorine? Where would the positive charge be right now? The one on the bottom. Because this one only has 3 bonds. You can see it clearly here that that carbon only has 3 bonds instead of 4. So it's positively charged, it's a mole. So then we bring back in our AlCl4 minus. What does the chlorine do? What does it grab? It grabs the hydrogen. And as it grabs the hydrogen, the 2 electrons from the hydrogen fold back in to restore that double bond. So it grabs the hydrogen. I point that better towards the hydrogen. It grabs the hydrogen, and then the 2 electrons go back in to restore the double bond. And so you end up with this again. Plus HCl plus AlCl3. That's it. So if you show the 3 double bonds, you'll see exactly where your positive charge is at. However, Cambridge does not require you to do this. They allow you to just do the ring with the positive charge and say, we know this happens. Yes.
Are they going to ask us to specifically answer it this way, or?
No. You can do it this way. I just wanted to show you, for those of you that need to see octet row being satisfied, and how the charges come about. This proves it a little bit better. However, these electrons are not stuck in place. So that's why they do the delocalized ring system. All right, let's go ahead and take a look at our next checkup from the textbook. It says, draw the displayed formula of a tri-substituted halogen produced if methylbenzene is added to excess bromine. So I've got methylbenzene, I've got excess bromine, and they said to tri-substitute it. So where would I put the bromines? 2, 4, and 6. So it would be this, this, and this. Only because we're being told we have to put 3 on. How would the reaction have been different if we changed the conditions and instead of the catalyst, we used UV light? How would the reaction be different? The bromines would not add, they would not substitute into the ring. Where would they substitute instead? Would substitute into the side chain instead of the ring. And so what would the name of this mechanism be? It's just electrophilic substitution. Or sorry, this would be free radical substitution. Because part E doesn't exist. Just saying this part. Free radical substitution. And the top one here was electrophilic substitution. On the next slide is some Cambridge questions. Here we go. Write an equation to show the formation of the electrophile during the reaction between bromine and benzene. So how would I show the electrophile being formed? How do I generate the electrophile? They didn't tell me what catalyst to use, so does it matter? Yes, go ahead, Fred. AlBr3 plus what? Br2 goes to AlBr4 minus and Br plus. Hey, I said it didn't matter, but what was the other option? Because we've been using aluminum a lot, and there was another option. Iron. This could have easily have been FeBr3 plus Br2 goes to FeBr4 minus plus Br. Same thing. So you can use either catalyst. So in the next question, they ask you about the mechanisms in a unique fashion. They ask you to draw the structure of the intermediates. And this is actually a continuation question from the bell work and the early questions we did today. I kind of just put it into different parts of the lesson. This is an electrophilic addition. What would the intermediate look like? In an electrophilic addition, what would the intermediate look like?
Make it go thing.
Go back all the way. All the way. Here. What does the intermediate look like? It's a carbocation. Somebody said it. And because this is equivalent, does it matter? Because it's CH2, CH2. Does it matter which side gets the positive charge? It does not. So you would do H2C, CH2. I would put my Br. And then the way that I have it drawn, where would my positive charge be? Left or right? Left. That's my carbocation. And for the second one, what would the intermediate look like?
Okay, what's the H? Yeah.
Broken ring,
Oh yeah. That.
H, Br, like that. With the H and the Br both on the same carbon at the time before you remove the hydrogen for the second step. So, I think this question, I think it's from an older test. I feel like this is an easy question, but we could get it wrong. Suggest why the product of the reaction between bromine and benzene is still unsaturated.
I forgot what that means.
That's why we could get it wrong.
The
It's unsaturated because benzene still has double bonds.
And that's 3 marks? Or is it 3 marks?
No, the 3 marks is for this, and that.
Okay.
So 1, 2, 3. All right. Yes.
You mean just write double bonds for like the last one, or do you have to specify it, like because it still has?
Well, you need to specify why benzene is unsaturated. Benzene has double bonds.
Yeah, but I'm saying can you just write double bonds and that's it?
I'd probably write the full thing. Okay. So there's more. Nitration. The mechanism of nitration. So for all the different substitutions we're doing today, which were first the halogen substitutions. Go ahead. And now the NO2 substitution. The actual type of reaction is exactly the same. Like the mechanism is the same. However, here, the generation of the electrophile reaction, I would say it's a little bit more complicated. And yes, you do need to remember it. Yep. This is how nitric acid reacts. Concentrated nitric acid reacts with concentrated sulfuric acid. This reaction is a little bit crazy. So I'm going to write it in steps at the bottom, but you just have to memorize this at the top. So how does that even happen? How do you get those products is the question. So HNO3 plus H2SO4 plus another H2SO4, right? Instead I needed to look up to make this happen. Okay, so this actually reacts in an acid-base reaction. And it turns out that the HNO3 will get an extra hydrogen from the sulfuric acid, meaning that when nitric acid and sulfuric acid are mixed together, the sulfuric acid will force the nitric acid to act as a base. That's crazy. And so you end up with H2NO3 plus HSO4 minus plus H2SO4 right now. That's what we have. But this is unstable. H2NO3 plus is unstable. And it breaks apart into 2 products. And those 2 products happen to be very similar to what we do with the H2CO3. And you get NO2 plus and H2O. NO2 plus and H2O. And then you've got all that going on. NO2 plus H2O plus HSO4 minus plus H2SO4. So right now this is what I got. NO2 plus H2O plus HSO4 minus plus H2SO4. This other sulfuric acid will give the water its H plus. So this will transfer here, like that. And so that gives us NO2 plus H3O plus HSO4 minus plus HSO4 minus, which is what we have here. This is the process of how that happens. Do you need to memorize this process? No. As usual, I like to give you more information than the bare minimum required to help aid your understanding of how did this even happen in the first place. I think it is interesting, first of all, to note that sulfuric acid forces HNO3 to become a base. I think that's very interesting. And then H2NO3 plus, because it's not stable, it actually looks just like H2CO3 and breaks up just the same way as H2CO3. Except because it has a positive charge, instead of having, carbon dioxide, CO2, you get NO2 with a plus charge as a result. And then after that, the sulfuric acid protonates the water, the other sulfuric acid. So you get this variety of products. This is something you will have to memorize, that reaction. Because if you got nitration as your electrophilic substitution mechanism, generation of the electrophile is mark 1. So you have to know how to get the NO2 plus that's going to go on the ring. After getting the NO2 plus, everything else is the same as all the other electrophilic mechanisms. So the steps are the same. And that would be, the ring grabs the electrophile, then you've got your broken ring with the positive charge, then your water this time would grab hydrogen, hydrogen will go there, and then you get NO2 plus H3O plus as a result. So that's nitration, the mechanism for nitration. Okay, there's more. Told you there's a lot. We were going to do a lot with you today in next class. There's another one. You could add more to your benzene ring, so more reactions. I did say there'd be like 7 today. This is how you get a methyl group on your benzene ring. And so there's something called a Friedel-Crafts, and yes, that's the scientist who came up with it. Friedel-Crafts alkylations and Friedel-Crafts acylations. This is alkylation, it's adding carbon chains into your ring. And it's technically substituting, because although it looks like an addition, you are swapping out for a hydrogen. This is called an alkylation, because alkyl groups are CH3 groups. And so it would look like this, where you have a benzene ring, you have R is some kind of chain of carbons. You have the same catalyst, so the reaction actually happens exactly the same. But instead of adding a halogen into your ring, you add a chain of carbons into your ring. And then this is how it's going to look. So let's say I have this plus CH3, CH2Cl, AlCl3. What would my product be? It would be the benzene ring. CH2, CH3. How? Actually happens almost exactly the same way as everything else you've seen. The AlCl3 will grab this chlorine, right? And if it grabs this chlorine, it would make CH3, CH2 what charge? What would that look like? It would be AlCl3 plus CH3, CH2Cl. It would become AlCl4 minus. So what does the CH3, CH2 have to be? It loses the chlorine. What charge does it have? It is plus. That's your electrophile. So it forces your alkane group to take on a positive charge, which means it acts as the electrophile. So it's going to get added into the ring. You should write this down. Yes, this is a reaction for a flashcard. It is on the back. There's a lot of electrophilic substitutions. And they all have the same key idea that you're grabbing the halogen, making an electrophile, and then that electrophile substituting in the ring and kicking out a hydrogen. So there's an alkylation. There's also an acylation. Alkyl means carbon chain. Acyl group. You may or may not remember acyl chloride from unit 5. There's going to be a lot of acyl chlorides in this unit. There's a whole lesson for acyl chlorides. I'm giving you a little bit of time. Okay, ready? No?
Yes.
Yes? All right, acylation, same thing, but instead of adding a carbon chain, you are now adding a carbonyl group into the ring. And so how does this look? So this is another reaction that's an electrophilic substitution. This is if you have a acyl chloride, so something like this. And you've got that catalyst. The AlCl3 will take the chlorine, and what will be the electrophile? That. So the group would get added to the ring at the carbonyl group. This is a way you can make a ketone. So if you need a method to get a ketone into your benzene ring, you use an acylation to do that, which means you're using an acyl chloride. Remember, acyl means this. Backwards. Another electrophilic aromatic substitution. So let's say you had this, just as an example. What would be your product? It has to add here at the double bond. So the double bond has to be on the first carbon from the benzene ring. So it would be like this. And this is 1, 2, 3. So 1, 2, 3. That's how it would add. Once you have a ketone on that ring, you could change it to an alcohol with a reduction. Like there's other things you could do with it from there. After you change it to an alcohol, you could eliminate it with a dehydration and get an alkene. The options for you creating your reactions are boundless. Yes, synthesis will be coming. Not yet, but it's coming. That's why we'll have group competitions and mini assessments. Yes.
So does the CL just go to HCl?
Yes. And then you get AlCl3. Okay, so how would this look as a mechanism? Let's take a look at the mechanism for this. Friedel-Crafts alkylation, benzene, CH3, CH2Cl, and AlCl3. How would this look for a mechanism? Generate your electrophile. How do we generate it?
Like I do the ALCL3.
So it would be CH3, CH2Cl plus AlCl3. And what do you get as your products? AlCl4 minus CH3, CH2 plus. And it's where that plus charge is. That's what's going to be going to the ring, right? So you first have to generate your electrophile. Then we do the reaction. what's getting put to the ring. From where? From the electrons, right, which are in the ring, to here, to the carbon. And so you end up with this. Where my plus charge is, I'm going to put my CH2, CH3 next door, and a hydrogen. What do we do next? And remember, the mechanism is the same every single time. Now the AlCl4 minus is coming in and grabbing the hydrogen. And the 2 electrons that connected the hydrogen to the ring have to go somewhere. They go back into the ring every time. And you get the final product. That's it. Another electrophilic aromatic substitution. We got a couple more reactions to cover today. How very exciting. I think we'll have enough time. I think we have enough time. That's so exciting. The more we do today, the less you have to do on Thursday. That's the thing.
That's a heavy.
That's a different thing. Yes, the way you approach life. Is it the more I do today, the less I have to do tomorrow? Or is it put this off today and then I have to do more tomorrow? Which way of life do you go by? You can guess mine. Mine is get everything done possible to have as much time off afterwards as possible. All right, ready? No? Okay, I'll pause. Do you want to see this mechanism one more time?
No.
Or do you want to move to the last reaction? What? Move on? Are we good with the mechanism?
Well, this one
We
kind of
understand.
different.
Oh, but somebody said it was different. So maybe we should do it.
This looks kind of different.
Okay, so paper 4 question. It's an acylation. They give you this reactant, this product, write a reaction to generate that electrophile. What do we do here? CH3, COCl plus AlCl3.
Which thing? Oh, that thing.
Yeah, that thing. So what are my products for 1 mark? AlCl4 minus, right? And what's the other one? CH3, CO. Yeah, absolutely. And probably more appropriate at the end. Just I'm showing it over the whole thing, but more appropriate to have over the carbon, like to indicate that's where it is. Okay, so that's step 1. Now they want us to do the mechanism to go from this to this. Now, interesting note, they're putting the acyl group on carbon 4, not on carbon 2. Does it make sense why that's actually most appropriate?
Yes.
Like,
it-
why not have chosen to put it
Yes.
here?
No.
What's the issue?
It's like-
So this is called kind of like interference. They're too close to each other. There's a fancy word for that organic chemists use called steric hindrance. Hindrance, yeah, it hinders from going to that position. So it's actually more appropriate if you have a large bulky group, for a large bulky group to go to carbon 4 instead of carbon 2 or 6, so that it has more space. So it's because spaced too close. In easier words, spaced too close. So big bulky groups usually go across, not right next to. Whereas small groups, like, single atoms, will go right next to easily. It's just a single atom. So I did want to bring that up because there is a reason they're choosing to put this on carbon 4 across, not on carbon 2 or 6. Okay, so do this mechanism one more time. on the next slide. Same mechanism, just different electrophile. It's always the same mechanism if it's electrophilic substitution. Let's try it. Our electrophile here is what? CH3, CO plus, right? So what do? Imagine this is 3 marks. What do?
Thing from ring to thing.
Ring, grab, plus, right?
And then broke.
Ring. Here we don't have a choice. It doesn't really matter, but like I want it there. We don't have a choice. We have to put the acyl here, right? Does that make sense? This is the hydrogen, and then that would be the missing carbon right there. Then the carbon that has 3 bonds would be the one at the top. Now what? The AlCl4 comes back in, grabs the hydrogen, and those 2 electrons restore the ring. We get this. That's it. Other products are AlCl3, restore the catalyst, and HCl. You got it?
Yeah.
Was it really different from all the other ones we did? The only thing that was different is that you had to put in a specific position because you were told which position to put it in. All right, the next 2 slides are our final 2 flashcard reactions for the day for benzene. I told you we were doing like 7 reactions in a mechanism today.
And Benzene did a lot of stuff, shouldn't it?
You did so much in the 2.
Okay,
7.
That's really good.
yeah,
You did 7?
7 reactions, yes.
Oh,
Chlorination, bromination, nitration, alkylation, acylation,
You don't want to understand.
and now 2 more, right?
Right?
By the way, it's called bromination. It's called chlorination. You know how there's a coronation? Chlorination.
That's a chlorine.
Instead of coronation, it's chlorination. All right, last 2 reactions. Can I move on? No? Okay. Benzene does 1 addition reaction, and this is it. The same conditions, H2 with nickel, platinum, and high temperature. You do not have to give a specific temperature for this one or specific pressure.
Very finely
And you
divided.
don't have to say very finely divided nickel. For Cambridge, you just have to say the catalyst and that it's high temperature. So what this does is it actually turns your benzene straight up into a cyclohexane. It adds to all 3 double bonds. So obviously you need excess hydrogen for it to happen. There are 3 H2 here, but excess hydrogen. This will change benzene all the way to cyclohexane, removing essentially all double bonds. High temperature, H2, nickel, platinum. We'll do it. And this is a reaction you are just expected to know. And it is the same as a regular addition reaction. H2, nickel, platinum, breaks the double bond, adds 2 hydrogens. This does it to the whole ring. Yes.
So it might be covered later, but like, what does something like CR207 do to like
To what? Benzene?
benzene?
Nothing.
Okay.
Nothing.
Okay.
Nothing. Neither does KMNO4. Because benzene, it won't break it this way. It breaks the regular alkene. All right. Oh, and that brings me to the last reaction of the day, KMNO4. All right, number 7. Here we go. If you have KMNO4, it will not react with benzene. But what it will do is something crazy. And you can look up the mechanism for this yourself. I don't really know what it is. I just know this is crazy. For however long your alkane chain is, it literally gets rid of the whole thing, breaks it off, and replaces it with benzoic acid. So KMNO4, no matter what, your side chain is. If you've got ethyl, You've got KMNO4, and it is dilute sulfuric acid. It changes your side group from whatever it is, if it's an alkane group, to benzoic acid, to a carboxylic acid. You can look up the mechanism. I do not know. Just does it. Does that every time. I believe there's a special condition for this one you are expected to know. Let me read it word for word from here. Complete oxidation of the side chain. So this is number 5 on the reaction sheet. Using hot alkaline KMNO4 and then dilute acid. So it's hot, alkaline. They want you to know it in this order. KMNO4 and then dilute acid. So first, it's hot base with KMNO4, and then that's after step 1. Then you add acid to it. I think in the first step you end up with COO minus, like a carboxylate, and then you acidify it to get to the COOH. So this does have specific conditions. I put them word for word from the syllabus into the flashcard paper so that you have it.
The reflux
What?
and the reflux.
Yeah, reflux. Well, I mean, they didn't write it here, so that means they don't expect you to have to write it in your response. How they write it here is how they want you to remember it. But it is with reflux. So no matter what, however many carbons long it is, you completely oxidize it. You get rid of all the carbons. They go out into your reaction mixture stomach. And you replace it with benzoic acid. 1 carbon, still blood oxygen, OH, no matter what. That's your final reaction for the day. Let's take a look at a couple practice questions before we go. Copying complete 2 equations can be shown to do alkylation, acylation. Just do the products of this one and we'll be done on this slide. So this would be benzene. By the way, you can always write benzene skeletal. You do not have to write it displayed or structural for Cambridge. You can always write benzene skeletal. So then what would my product be here? For C6H6 plus CH3CH2 CH2Cl.
Benzene and then CH2CH2.
Yeah, like that.
Yeah.
And this one?
Thing.
No, yeah, it's
How many carbons?
CO.
5. And if I wanted to change the top one to benzoic acid, how could I do it? Hot alkaline KMNO4, step 1. Step 2, dilute acid.
Alkaline is the basic.
Alkaline is basic. So you first, I think that's what I said, I think you first get COO minus, like as a result of the initial breakage. And then after that's done, you acidify it to get to benzoic acid. So it's a base first and then the acid.
Normally it is step 3.
It usually is acidic KMNO4 we use, but here we're using alkaline. All right, so we finished part 2. Yay! Next class, that means we get to do phenol. Reaction with phenol. All right, so remember that the 2 and 3 homework, we're not finished part 2 today. I'm giving you extra time. There's a lot of homework, if I recall. So that's going to be due on Monday, along with part 3. So I'm doing your next homework check next Monday for parts 2 and 3. And then next class, I'm going to give you the schedule on what's going down for team competitions and mini assessments for organic chemistry. Expect they start next week. Approved. Yes, why?
I didn't explain it to you.
Oh my God. So today was like a brain dump of information.
Yeah. I mean, I actually understood.
Brain dump.